Assalamualaikum dear students. In today's lecture we are going to learn number theory and few algorithms related to division and modulus arithmetic. And this lecture covers the section 4.1 in the book, and 4.1 is about divisibility and modular arithmetic. So first of all, divisibility. So when we divide one integer by another integer which is non-zero integer, then the quotient may or may not be an integer. For example, if we divide 12 by 3, we have a quotient 4 which is an integer, and when we divide 11 by 4, we have a quotient 2.75 and which is not an integer. So there is a definition of divisibility when we divide two integers a and b, where a is not equal to 0, then a divides b if there exists an integer c such that b is equal to ac. So there are a few points to be noted. When a divides b, we say that a is a factor or divisor of b, and that b is multiple of a. Right? So the notation a divides b denotes that a divides b. Okay, we read this notation as a divides b. And if a divides b, then b over a is an integer, right? If a divides b, then b is equal to a with ac, and this implies b over a is equal to c, and c is an integer, so the b over a is an integer. And another remark, if a does not divide b, then notation for this is like this. A does not divide. This cross means does not divide b. Now there is an example. Determine whether 3 divides 7 and whether 3 divides 12. Now 3 divides 7, we just need to check 7 over 3 is an integer or not. Now 7 over 3 is not an integer, therefore 3 does not divide 7. Now 12 over 3 is an integer, so this means 3 divides 12. Now there are few properties of divisibility. Let a, b, c be integers where a is not equal to 0. Then property number 1, if a divides b and a divides c, then a divides b plus c. Property number 2, if a divides b, then a divides bc for all integers c. Property number 3, if a divides b and b divides c, then a divides c. If a divides b and b divides c, then a divides c is reflexive property. Transitive property, right? Transitive property of relations. And we have already discussed it in the chapter of relations, and we proved this as well. So proof for the property number 1, if a divides b and a divides c, by definition of divisibility, if a divides b, there must be some integer such that b is equal to a multiplied by integer. So let that integer be s, then b is equal to a into s. And since a divides c, so c can also be written as a multiplied by some integer, and let t be the integer such that c is equal to at. Now sum of a and b, b and c, b plus c is as plus at. Now let's factor out a, and we have s plus t inside, so a multiplied by s plus t. Since s is an integer, t is an integer, so s plus t is also an integer, so b plus c is equal to a multiplied by some integers, and this implies a divides b plus c. Similarly, we can prove part 2 and part 3. For part 2, we'll see if a divides b, this is given. If a divides b is given, and we have to prove that a divides bc where c is an integer. Now similarly, a divides b implies there is an integer s such that b can be written as a into s, right? And so bc is equal to a s c. Now, or it can be written as a into sc, and this can be written as a into k, where k is equal to sc, and since s and c both are integers, so k is also an integer, and this implies bc is equal to a multiplied by some integer. So by definition of divisibility, this implies A divides BC, right? So similarly, you can prove part 3 yourself. And next, there is a corollary. If A, B, and C be integers where A is not equal to 0, such that A divides B and A divides C, then A divides MB plus NC, where M and N are integers. Now, by the use of property 1 and property 2, we can prove this. Next, there is a division algorithm when an integer is divided by a positive integer. So keep this in mind. We are dividing by positive integers. There is a quotient and a remainder. So this is traditionally called the division algorithm, and you are already familiar with this algorithm. If A is an integer and D a positive integer, then there are unique integers Q and R, with R lies between 0 and D. R is greater or equal to 0, R can be 0, but R is less than D, that is this D, such that A is equal to DQ plus R. Here, D is called divisor, A is called dividend, Q is called quotient, R is called remainder. For example, if we divide 75 by 2, then how can 75 be written in this form? D here is 2, A here is 75, that is our dividend is 75 and divisor is 2. So 75 can be written as 2 into 37 plus 1. So this is Q and this is our R. And what happens when our A is negative? Because if we read the division algorithm again, A is an integer, so there is no condition on A. A is just an integer. It can be positive, it can be negative, but D is a positive integer. So let's see if A is negative and D is positive. For example, if we divide minus 101 by 2, then now A here is negative 101 and D here is 2. So negative 101, the first thing which comes into our mind, that it can be written as 2 into minus 50 and plus minus 50 multiplied by 2 is negative 100. So in order to make it minus 101, we just have to add negative 1. But see, there is a condition on R that remainder must be greater or equal to 0. It cannot be negative. So this representation is wrong. So let's see what is the correct representation. So minus 101, quotient will be negative, of course, in this case, because divisor is D is positive. So in order to make it negative, quotient must be negative. So 2. We will consider minus 51 instead of 50. So this will make it minus 102. And in order to make it negative 101, what we need to do, we need to add 1. So in this case, remainder is 1, which is the right expression. So always seek for positive remainder. So this is the key. That is why I consider the negative A. So what you need to do is you need to seek for a quotient for which we have remainder positive, right? Okay. Now there are two functions. Definition of function div, which is used for division, divide, and this is mod, which is short form of modulus. Q is A divided by Q is the quotient. So this is the relation between A and D, and we have Q. Q is the quotient when we divide A by D, right? So Q is the quotient when A is divided by D. So this is how we read it, and R is the remainder, A modulo D. So this modulo term is very important in our next segments in number theory. So right now we are just defining a function modulo A modulo D is the remainder when A is divided by D. R is the remainder when A is divided by D, and we read it as A mod D. So we will use this function later. So Don't forget this. Okay, next there are more examples on division algorithm. So what are the quotient and remainder when 101 is divided by 11? So let's see. When 101 is divided by 11, we have quotient 9. That is, 101 can be written as 11 multiplied by 9 plus 2, right? So quotient is 9, and by the notation we just learned, 9, that is quotient, is the quotient when we divide 101 by 11, right? So 9 is the quotient when we divide 101 by 11, and the remainder 2 is equal to 101 mod 11, that is, when we divide 101 by 11, remainder is 2. Similarly, what are the quotients and the remainders when minus 11 is divided by 3? Now, keeping that rule in mind, that remainder must be positive, we have quotient minus 4 and remainder is 1. Next definition, congruence relation. Uh, we define the congruence relation for two integers if a and b are the integers. These are two integers and m is a positive integer. Okay, a, b can be any integers, right? M is positive integer, then a is congruent to b modulo m if a is then a is congruent to b modulo m if m divides a minus b. Whenever m divides a minus b, we say that a is congruent to b modulo m, and notation for this is a is congruent. This is the notation for congruence relation. A is congruent to b mod m. We say that a is congruent to b mod m. Okay. So when this relation holds, when m divides, this m divides a minus b, right? We say that a is congruent to b mod m is congruence and that m is its modulus. Two integers are congruent mod m if and only if they have the same remainder when divided by m. Okay, it makes sense because m divides a minus b means that we when we divide a minus b by m, the remainder is 0. Okay, now if we divide a by m and if we divide b by m, if both the cases in both the cases we have same remainder, then an division of a minus b by m will yield a remainder 0. Okay, so you must remember this result as well. Two integers are congruent mod m if and only if they have the same remainder when divided by m, right? If a is not congruent to b modulo m, then we write a is not congruent. Just cut this notation of congruence by a line. So a is not congruent to b mod m. So this line represents not congruent. Now there is an example of congruence relation. Determine whether 17 is congruent to 5 modulo 6. 17 is congruent to 5 modulo 6. Now before having a look at the congruence, let's try it, then I'll show you the result. What we need to check, 17 is congruent to 5 mod 6, right? Now m here is 6, a here is 17, b here is 5. So if this relation holds, if 6 divides 17 minus 5. Now see what is 17 minus 5? 17 minus 5 is equal to 12, and 6 divides 17 minus 5. So this means this is true. 17 is congruent to 5 mod 6. Now next, 14, 24 and 14 are congruent to modulus 20, whether 24 and 14 are congruent modulo 6. That is, what we need to do. So let's have a look at the first part. Here we go. 17 is congruent to 5 mod 6 because 6 divides 17 minus 12. And now 24 is not congruent because 6 does not divide 24 minus 14, that is 10. So here this is not a congruent relation. Now more on congruences. Let's have a look at this theorem. This theorem states that let m be a positive integer. So these signs are very important. M be positive integer. The integer a and b are congruent modulo m if and only if there is an integer k such that a is equal to b plus km. So this is quite straightforward from the definition. First of all, let's assume which is given. That is given as a is congruent to b mod m. So let's assume this. And we have to prove that this is if and only if case, so we need to prove p implies q and q implies p both. So first we assume that a is congruent to b modulo m, and we'll prove that there is an integer k such that a is equal to b plus km. Now by definition of congruence relation, if a is congruent to b mod m, then what happens, m divides a minus b. Now by the definition of divisibility, m divides a minus b means a minus b can be written as multiple of integral multiple of m multiplied by some integer k, where k belongs to okay. Now what does this mean? This implies a is equal to b plus kn. Okay, this is what was required. And conversely, similarly, you can prove the converse. Conversely, if there is an integer k such that a is equal to b plus km, so km can be written as a minus b, and this implies m divides a minus b. And if m divides a minus b, then this implies a is converted to b mod m. So that's all for the proof. Now the relation between mod m and mod m notations. The use of mod in the congruence a is congruent to b mod m, and the function a mod m is equal to b are different. A is congruent to b mod m is a relation on the set of integers, and in a mod m is equal to b, the notation mod denotes the function. Now the relationship between these two notation is made clear in this theorem. Let a and b be the integers and let m be the positive integer, then a is congruent to b mod m if and only if a mod m is equal to b mod m. This is what we have already discussed in previous slides, that a is congruent to b mod m means m divides a minus b, and this happens if and only if remainder remainder when we divide a by m is equal to the remainder when we divide b by m. Okay, so this is what this statement means. So this represents the relation between these two mods. Congruence of sums and products. Now there is another result. Let m be the positive integer. If a is congruent to b mod m and c is congruent to d mod m, then we can add both the congruences, and we'll get another valid congruence relation. Now by adding left hand side and by adding right hand side, we have a plus c is congruent to b plus d mod m, and multiplying both the congruence relations, we have ac is congruent to bd mod m. Now you can prove these results. These are straightforward steps, and only use the definition. Now let's see how can we apply in the example. 7 is congruent to 2 mod 5 because 7 minus 2 is 5 and 5 divides 5, and 11 is congruent to 1 mod 5 because 11 minus 1 is 10 and 5 divides 10. So let's add both the congruents. We have 18. 7 plus 11 is 18 according to this theorem, is congruent to 1 plus 2, which is 3 mod 5. So let's verify the result. 18 minus 3 is 15 and 5 divides 18 minus 3, that is 15. So this is a valid congruence relation. Again, multiply both the congruence relations. We have 7 multiplied by 11 is 77, and 2 multiplied by 1, there must be the sign of multiplication. 2 multiplied by 1 is 2 mod 5. So see if this relation is valid. 77 minus 2 is 75. and 75 is divisible by 5, so 75 is congruent to 77 is congruent to 2 mod 5. Now, algebraic manipulations of congruences multiply both the sides of valid congruence by an integer preserves validity. That is, if A is congruent to B mod M, then we multiply both the sides by an integer C. The result will still valid. That is, this is a valid congruence relation. CA is congruent to CB mod M. Similarly, if we add an integer to both the sides, we have a valid congruence relation. And division usually does not hold, and it may or may not hold. So we cannot say that division is valid. Division is a congruence by an integer does not always produce a valid congruence. So let's have an example. If we have a congruence relation 14 is congruent to 8 mod 6, let's multiply this congruence relation by 2, like 14 multiplied by 2 is congruent to 8 multiplied by 2 mod 6. So first of all, let's check the validity of this congruence relation, that is 14 is congruent to 8 mod 6. 14 minus 8 is 6 and 6 divides 6, so this is valid. Now multiplying both sides by 2, we have 28 is congruent to 16 mod 6. So 28 minus 16 is equal to 12. So 6 divides 12, that is a valid relation. Now if we add 2 to the both sides, so we have 14 plus 2 is congruent to 8 plus 2 mod 6. Now 14 plus 2 is 16 and 8 plus 2 is 10. So this is a valid congruence relation because 16 minus 10 is 6 and 6 divides 6. So this is a valid relation. Now for divisibility, let's divide this congruence relation by 2. It does not produce a valid congruence relation, as 14 over 2 is 7 and 8 over 2 is 4. Now 7 minus 4 is 3 and 6 does not divide 3, so 7 is not congruent to 4 mod 6. Now computing the mod m functions of products and sums. Now there is a result which is going to be used several times in later arithmetic of modulus. So let m be a positive integer and let a and b be integers. Then a plus b mod m. Now what does this represent? This represents the remainder when we divide a plus b by m. And this is equal to a mod m, that is remainder when we divide a by m, plus the remainder when we divide b by m mod m. Okay, and ab mod m is equal to a mod m into b mod m, right? Next, arithmetic modulo m. Let Zm be the set of non-negative integers less than m is equal to 0, 1 to m minus 1. Less than m, that is 0, 1 to m minus 1. The operation addition modulo m, this addition with subscript m is called addition modulo m, and this is defined by a plus addition modulo mb is equal to a plus b mod m. That is, when we add both the numbers, what will be the addition modulo m? We'll first add and then we will divide by m, and the remainder will be the answer. The operation dot m, that is multiplication modulo m, is defined as a dot mb is equal to ab modulo m, that is multiply both the integers first and then divide by m, and remainder will be the answer. This is called multiplication modulo m. So let 7 plus 11 under addition modulo 7 plus 9 under addition modulo 11, and what is the value of 7 multiplied by 9 under multiplication modulo 11. So let's solve this. First we add 7 and 9 in a usual manner, and answer is 16. Now divide 16 by 11, the remainder is 5. So 7 plus 9 under addition modulo 11 is equal to 5. Similarly, 7 multiplied by 9 is 63, and now divide it by 11 and remainder is 8. So 7 multiplied by 9 under multiplication 11 under multiplication modulo 11 is 8. Now there are few properties which arithmetic modulo m holds, that is addition modulo m and multiplication modulo m holds in the set Zm. Now what is the set Zm? This consists of all the non-negative integers less than m, that is 0, 1, 2 up till m minus 1. Now if AV belongs to, if we belong to Zm, then addition modulo m of a and b and multiplication modulo m, a and b belongs to Zm. So this is the Closure property under addition and multiplication modulo m. Similarly, addition modulo m and multiplication modulo m is associative, and commutative law also holds. So identity element, that is the element 0 and 1 are identity elements for addition and multiplication modulo m respectively. So if a belongs, that is if a belongs to Zm, then a plus addition modulo m 0 is equal to a. So it returns the element itself, the integer itself. Therefore 0 is called the additive identity. And when we multiply any number by m 1, then it returns a. For example, if we have the set Z3, this consists of the elements 0, 1, 2. Right? M here is 3, so 0, 1 up till m minus 1, 0, 1, 2. Now let's have 2 plus 3, 0. Okay, so addition of 2 and 0 modulo 3 is equal to 2. 2 mod 3, that is when we divide 2 by 3, so remainder is 2. So this is already less than 3, so answer will be 2. Similarly, if we multiply 2 by 1, and this will give us again 2. Okay, so this is how this works. Now arithmetic modulo m additive inverse. Now again let's have the set Z3, which is equal to 0, 1, 2. Okay, now we need to find the additive inverse. So what is the additive inverse of 0? This is always 0. And what is the additive inverse of any other element apart from 0 is m minus a. So m here is 3 and a here is 1. So what is the inverse of 1? So 1, 3 minus 1, that is 2, is equal to. Now add both these, add both 1 and 2, we have 3. Now divide 3 with, answer is 0, remainder is 0. So inverse of a under addition modulo 3 is 2. Okay, that is inverse of a under modulo m addition modulo m is equal to m minus a. Right? Now I hope you got it. Now the multiplicative inverse have not been included since they do not always exist, right? And similarly distributive laws holds, so you can verify this yourself.